I want to tell you something about science that most people misunderstand. Science is not a collection of answers. It is a practice of asking questions. And the questions it cannot answer, the stubborn, resistant, embarrassingly simple questions that have defeated centuries of brilliant minds, are not evidence of failure. They are evidence of how deep the universe goes. Every time we answer one question, we find three more beneath it. Every time we think we understand something, the understanding reveals a new layer of not understanding. The edge of knowledge is always further than it looks. And the questions that live at that edge, the things science genuinely, honestly cannot explain, are, I think, the most interesting things in the world. Tonight, I want to take you through 100 of them, not quickly, not as a list of bullet points, as a slow journey through the frontier, through the places where the maps run out, where the confident language of textbooks gives way to phrases like "we don't fully understand" and "the mechanism remains unknown" and "this is an open question." I find those phrases beautiful. They are honest. They are rare. In a world that prizes certainty, the admission of genuine not knowing is a kind of courage. So settle in, let the questions wash over you, not to be solved, just to be felt, just to be known. The mystery is not a problem to be fixed. It is a companion. It has been with us since the first human looked up at the sky and wondered what the lights were. It will be with us for as long as we keep asking, which is, I hope, forever. The mystery of consciousness, what it means to be aware. Why does the brain produce consciousness? This is, many philosophers and scientists argue, the hardest question in all of science. Harder than dark matter, harder than the origin of the universe. Because at least with dark matter and the Big Bang, we know what kind of answer we are looking for. We are looking for physical explanations, for particles and fields and equations. But with consciousness, with the fact that there is something it is like to be you, we don't even know what kind of answer would count. The brain is extraordinarily complex. 100 billion neurones, 100 trillion connections, electrochemical signals propagating through networks at extraordinary speed. We can describe the neural correlates of consciousness, the brain states that accompany particular experiences, but we cannot explain why any of this produces experience at all, why it doesn't all happen in the dark without anyone there to feel it. This is called the hard problem of consciousness, named by philosopher David Chalmers in 1995, and it remains 30 years later completely unsolved, not partially solved, not mostly understood, unsolved. The most fundamental fact about our existence, the fact that we experience anything, is not explained. Why do we sleep? This question seems like it should have a simple answer. We sleep because we're tired. We sleep to rest. But what does rest actually mean biologically? Why does the brain, which continues to be active during sleep, sometimes more active than during wakefulness, need a period of reduced interaction with the external world? We have some hypotheses. Sleep consolidates memories. The brain seems to replay and strengthen the neural connections formed during the day. Sleep clears waste products. The glymphatic system, a waste removal system in the brain, is significantly more active during sleep. It flushes out metabolic waste products, including the protein fragments associated with Alzheimer's disease. Sleep regulates hormones, immune function, and metabolism. But none of these individually or together fully explains why sleep is absolutely necessary, why going without it kills you faster than going without food, why every animal we know of sleeps, even insects, even nematode worms, why the brain during sleep is not simply idle but doing something specific and structured. The function of sleep, the reason it is essential in a way that nothing else can substitute for, is not fully understood. We spend a third of our lives doing something we don't fully understand. What is the purpose of dreams? Dreams are extraordinarily strange. You are unconscious, and yet you experience vivid, detailed, emotionally charged narratives, often involving impossible things, often involving people, in situations that could never happen, often frightening, often pleasurable, often bizarre, and you believe them while they are happening. You believe them completely. You have no sense that this is unusual. Only upon waking do you recognize the strangeness. Freud thought dreams were the disguised expression of repressed wishes, the unconscious speaking in symbols. Modern neuroscience is more skeptical. The activation synthesis hypothesis proposed by Hobson and McCarroll in 1977 suggests dreams are the brain's attempt to make sense of random neural activity during REM sleep, the brain generating a story to explain the signals it is receiving from its own activity. But neither theory fully explains the content of dreams, why they are so often meaningful to the dreamer, why certain dream themes, being chased, losing teeth, flying, being unprepared for an exam, are nearly universal across cultures, why recurring dreams exist, why some dreams seem to solve problems the waking mind cannot. The function of dreaming and whether it has a specific function at all remains genuinely unknown. How does anesthesia work? This one surprises people. Anesthesia has been used in surgery since the 1840s. Hundreds of millions of people have been anesthetized. It is one of the most commonly performed medical procedures, and we don't fully understand how it works. We know what anesthetic drugs do at the molecular level. They interact with specific receptors, they affect ion channels and cell membranes, they modify the electrical activity of neurons, but we don't understand why and how this produces the loss of consciousness. Why disrupting these particular molecular targets in these particular ways causes a person to be there conscious, aware, present, and then suddenly not there, not asleep, not unconscious in the way sleep is unconscious, simply gone, and then when the drug clears, there again, without any experience of the intervening time, without any sense of duration, without any dream, just there, gone, there. We can induce and reverse this state reliably. We can adjust the dose, we can monitor its depth, but the mechanism by which a molecule changes a person's state of existence, by which chemistry becomes consciousness or its absence, is not understood. What is the self? When you say I, when you refer to yourself, what are you referring to? The obvious answer, your body, your brain, the physical object that has your name. But the atoms of your body are replaced entirely every few years. Are you the same person you were 10 years ago? Your beliefs have changed, your body has changed, your memories are different and demonstrably unreliable, shaped by every subsequent experience. The person who was 7 years old, terrified of the dark, who fell off a bicycle and cried, "Is that you?" Or is there continuity that transcends the changing atoms and the changing mind? Philosophers have debated this for millennia. Derek Parfit, one of the most important philosophers of the 20th century, argued that personal identity is not a deep fact about the world, that the question, will this future person be me, is sometimes simply not answerable. Not because we lack information, but because personal identity is not the kind of thing that has a determinate answer. We assume there is a self, a continuous, unified, persisting entity, behind the thoughts and feelings, doing the experiencing, but neuroscience cannot find it. The brain has no center, no place where experience is gathered and processed by a unified observer. It is a distributed, parallel, massively interconnected system. Where is the self in that system? We don't know. We don't even know if the self is a thing to be found, or a story we tell, a narrative constructed after the fact to make sense of the thoughts and feelings that arise in a brain that has no center. The self may be the last great fiction, or it may be the most fundamental reality. We cannot tell the mysteries of life, what living things do that we cannot explain. How did life begin? We know, roughly, when approximately 3.7 to 4 billion years ago, shortly after the Earth had cooled enough to have liquid water, we know roughly where, possibly in deep-sea hydrothermal vents, possibly in shallow warm pools on land, possibly at the interface between water and minerals. We know what it must have produced: self-replicating molecules, molecules that could copy themselves. And that copying was imperfect enough to produce variation, which natural selection could act on. We have hypotheses about how this might have happened. The RNA world hypothesis, suggesting that RNA, which can both carry information and catalyze chemical reactions, was the first self-replicating molecule. The metabolism first hypothesis, suggesting that chemical cycles analogous to cellular metabolism arose first and self-replication came later. The lipid world hypothesis, suggesting that the first step was the formation of cell-like membranes. But none of these hypotheses has been fully demonstrated. No one has created life from non-living chemistry in the laboratory. Not yet. The exact sequence of steps from chemistry to biology, from dead molecules to living cells, is not known. Why does evolution produce complexity? Natural selection is a simple mechanism: heritable variation, differential reproduction, change over time. It produces adaptations, features that improve survival and reproduction in particular environments. But why does it produce complexity? A bacterium can survive in environments that would kill a vertebrate. A virus can reproduce faster than any complex organism. Simplicity and generality are often adaptive. And yet life became increasingly complex over evolutionary time, from single cells to multicellular organisms, from simple nervous systems to brains with 100 billion neurons. Why? The evolutionary pressures that drive complexity are not fully understood. The transition from single cell to multicellular life, which happened multiple times independently in the history of life, involved a fundamental change in the unit of selection. How this happened and why it was adaptive is not completely explained. What determines the size of species? Why are mice small and elephants large? This seems trivial, but the scaling of body size across all of life follows remarkably consistent mathematical patterns. Metabolic rate scales with body mass to the power of 0.75, not 0.5, not 1, Linden C. Wu, across more than 20 orders of magnitude in body size, from bacteria to blue whales. This pattern, called Kleiber's law, is extraordinarily robust, and the explanation for it is contested. Different theoretical frameworks based on fractal networks, on optimal resource distribution, on surface-to-volume relationships predict the value 0.75 from different assumptions, which means the explanation is not settled. The mathematical regularity is clear. The reason for it is not. How do cells know their position in a developing embryo? A fertilized egg divides and divides again and again And at some point, through processes that are only partly understood, different cells develop different identities. This cell becomes liver. This one becomes brain. This one becomes the tip of the ring finger. How does each cell know what to become? We know about morphogen gradients, chemical signals that vary across the embryo, providing positional information. We know about gene regulatory networks, cascades of gene activation and suppression that establish cell identity. But how all of this information, the gradients, the gene networks, the mechanical forces, the cell-cell communication, is integrated into a coherent, reproducible body plan is not fully understood. The embryo develops with extraordinary reliability. Given the same genetic information, the same environmental conditions, the same basic chemistry, you get the same body over and over. Every finger in the right place, every organ of the right size. The robustness of development, its resistance to errors, its ability to produce the same outcome despite variation in the inputs is remarkable and not fully explained. How do animals navigate? We talked about this briefly in the context of migratory birds, but let me expand. Birds navigate by magnetic field, vistas, landmarks, by smell. They integrate multiple sources of information and make navigational decisions with extraordinary precision across thousands of kilometers, returning to the same nesting site year after year. How the magnetic sense works at the neural level, how a bird's brain extracts directional information from the magnetic field and uses it to navigate is not fully understood. The physical mechanism, cryptochrome molecules in the eye, possibly entangled electrons, is hypothesized, but not confirmed. The neural processing, how the magnetic information is integrated with visual, olfactory, and memory information to produce navigational decisions, is largely unknown. And birds are just one example. Sea turtles navigate across thousands of kilometers of open ocean to return to the beach where they hatched. Monarch butterflies navigate 4,000 kilometers to a forest in Mexico they have never been to. Using a time-compensated sun compass with a brain smaller than a grain of rice, how? We have fragments of an answer, not the whole story. What causes aging? Every cell in the human body contains the information for life. The DNA in every cell is the same. The machinery of every cell, the ribosomes, the mitochondria, the cell membrane is maintained and repaired, and yet the body ages. Organs deteriorate. Tissues become less functional. Systems fail. Eventually, why? Multiple theories. Telomere, shortening the protective caps on chromosomes, becomes shorter with each cell division, eventually leading to cellular senescence. Accumulated DNA damage mutations accumulate over time, reducing cellular function. Protein aggregation, misfolded proteins accumulate in cells and tissues, impairing function. Mitochondrial decline, the energy-producing organelles of cells become less efficient. Epigenetic drift, the pattern of gene expression changes with age in ways that reduce cellular function. Inflammation, chronic low-level inflammation increases with age, contributing to tissue damage. All of these are real. All of them are part of aging. But whether any of them is the primary driver, the fundamental cause from which all others follow, or whether aging is the result of multiple independent processes occurring simultaneously, is not settled. The question of why we age, what aging fundamentally is at the molecular and cellular level, is one of the most intensely studied questions in biology, and it remains open. Why do we age at such different rates? Related but separate. Identical twins have identical DNA. and yet their aging is not identical. One may develop Alzheimer's disease, the other may not. One may develop cancer, the other may not. They may look dramatically different by the time they're 70, even though they started from the same genetic sequence. Why? The answer involves epigenetics, the pattern of gene expression, which is influenced by environment, behavior, stress, diet, relationships, but epigenetics only partly explains it. The stochasticity, the randomness of biological processes means that even identical twins raised in the same environment will differ because biological systems are noisy. Small random variations in molecular processes accumulate over decades into measurable differences in health and aging. How much of aging is genetic? How much is environmental? How much is simply random? We don't know with precision. The numbers change with every study. How does the immune system distinguish self from non-self? Every moment of your life, your immune system is making decisions. Is this molecule part of me, or is it foreign? Should it be attacked or left alone? The discrimination is remarkably precise. The immune system will destroy a bacterium, but not a red blood cell. Will kill a virus-infected cell, but not a healthy one. Will attack a cancer cell, but not a normal one. And sometimes when this discrimination fails, the immune system attacks the body itself. Autoimmune diseases, rheumatoid arthritis, multiple sclerosis, type 1 diabetes, lupus, the immune system killing what it should protect. We understand many of the molecular mechanisms, the T cell receptors, the MHC molecules, the clonal selection, but we do not fully understand how the immune system learns during development which molecules belong to the body, or why this learning sometimes fails, or why autoimmune diseases have become more common in recent decades as the immune system seems to be increasingly triggered by the wrong things. The rules by which the body decides what is self and what is other, the deepest immune question, are not fully known. The mysteries of the brain, what the mind does that we cannot track. How does memory work? We know that memories are stored in the brain. We know that long-term memories involve structural changes in synaptic connections, the junctions between neurons. We know that the hippocampus is involved in the formation of new long-term memories. We know that different types of memory, declarative memories of facts and events, procedural memories of skills and habits, emotional memories involve different brain regions and different molecular mechanisms, but we don't know how a specific memory, the face of a person, the taste of a food, the feeling of a particular moment, is encoded in the pattern of synaptic connections. We don't know how the brain retrieves a specific memory from the vast store. We don't know why some memories are vivid and detailed while others are vague and fragmentary. We don't know why emotional memories are stronger than neutral ones. We don't know why memories are not perfectly accurate, why we remember the gist rather than the details, why our memories are shaped by subsequent experiences, why we can be confident about memories that are completely false. Memory is the substrate of identity, of personality, of everything we know and are. And how it works at the fundamental level is not known. How does the brain produce language? Humans are the only species to have language, not communication. Other animals communicate. But language, the ability to combine symbols according to rules, grammar, to produce an infinite number of novel sentences, to describe things that are not present, things that are past, things that are hypothetical, things that have never existed, never will. How did this capacity arise? When did it arise? How is it implemented in the brain? Broca's area and Wernicke's area, two brain regions identified in the 19th century, are associated with language production and comprehension. But language involves much more of the brain than these two regions. It involves the motor cortex, the auditory cortex, the prefrontal cortex, the cerebellum, how these regions interact to produce fluent speech. How children acquire language, one of the most remarkable feats of learning ever documented without formal instruction, simply by being exposed to language. How much of language ability is innate, wired into the brain by evolution? How much is learned? These questions are not settled. Noam Chomsky proposed that humans have a language acquisition device, an innate grammatical structure. Others argue that language is learned through general cognitive abilities without a specific innate grammar. The debate continues, without resolution. What is creativity? Where do new ideas come from? When a mathematician sees the solution to a problem they have been stuck on for weeks. When a composer hears a melody in their head that has never existed before. When an engineer thinks of a design that no one has thought of, what is happening? Neuroscience can describe some of what happens in the brain during creative insight. The default mode network, a set of brain regions active during mind wandering when the mind is not focused on external tasks, is associated with creative thinking. The moment of insight is often associated with a burst of activity in the right temporal lobe, preceded by a period of reduced activity in the prefrontal cortex, the executive part of the brain, as if the conscious, rational, controlling mind needs to get out of the way for the creative insight to emerge. But what is the insight itself? What determines which combination of existing ideas will be combined in a new way? What makes some people more creative than others? Can creativity be taught, enhanced, inhibited? What is the difference between creativity and random noise? Between an insight and a mistake? The neuroscience of creativity is in its infancy. The answers are not there yet. Why do humans have such large brains? The human brain is approximately 3 times larger than you would expect for a primate of our body size. This is energetically expensive. The brain is 2% of body mass but uses 20% of the body's energy. Evolution does not produce expensive structures without a reason. So why did the human brain grow? The social brain hypothesis. Large brains evolved to navigate complex social groups. The cognitive niche hypothesis. Large brains evolved to solve ecological problems, to find food, to make tools, to plan for the future. The cultural brain hypothesis. Large brains evolved because of the cultural transmission of knowledge. Once humans could learn from each other, there was selection pressure for greater learning ability. The sexual selection hypothesis. Large brains evolved partly because they are attractive because intelligence is a fitness indicator. All of these have supporting evidence. None of them is definitively established. The exact selective pressures that drove the rapid expansion of the human brain in the last 2 million years, one of the most dramatic events in evolutionary history, is not known. How does the brain process faces? Humans are extraordinarily good at recognizing faces, better than we are at recognizing almost anything else. There are people who cannot recognize faces at all, prosopagnosia, or face blindness, because of damage to a specific brain region called the fusiform face area. But even the fusiform face area is not purely for faces. It is activated by anything that a person has become an expert at. Car experts show fusiform face area activation for cars, bird experts for birds. The face recognition system is extraordinarily sensitive. We can identify a person from a face we saw once years ago. We can detect minute differences between faces. We can read emotional information from facial expressions with remarkable precision. And we do all of this automatically, unconsciously, in a fraction of a second. How? The neural mechanisms by which the brain represents and recognizes faces, the specific computations being performed are not fully understood. What causes mental illness? Depression, schizophrenia, bipolar disorder, anxiety, obsessive compulsive disorder. These conditions affect hundreds of millions of people. They are the leading causes of disability worldwide. And despite decades of research, their causes are not well understood. We know that genetics plays a role. Mental illnesses run in families, and twin studies show significant heritability. We know that brain structure and function differ between people with and without certain mental illnesses, though the differences are not consistent or large enough to be diagnostic. We know that stress, trauma, and adverse childhood experiences increase risk. We know that neurotransmitter systems, particularly serotonin, dopamine, and norepinephrine, are involved. But we do not know the causal chain. Does depression cause low serotonin, or does low serotonin cause depression? How do genes interact with environment to produce the risk? Why do the same antidepressants work for some people and not others? Why does psychotherapy work? What is the relationship between the biological and the psychological in mental illness? These questions are not answered. The treatments we have are empirical, they work. For some people, for reasons we don't fully understand, the underlying neuroscience of mental illness remains one of the great mysteries of medicine. Why do humans laugh? All humans laugh. All cultures have laughter. It appears to be universal, involuntary, social, contagious. It is associated with positive emotions, with humor, with play, with social bonding. But its evolutionary origin and function are not fully understood. Why did evolution produce this particular vocalization? Why is it contagious? Why does hearing someone else laugh make you laugh? Why is it associated with humor specifically? What is the relationship between laughter and the cognitive process of finding something funny? Why is tickling, which is non-voluntary, which is induced by another person, associated with laughter? Even though it is not always experienced as pleasant, laughter is one of the most distinctly human behaviors, and we don't fully understand why we do it. The mysteries of physics, where the equations stop working. What is dark energy? We have discussed this before, but let me frame it differently tonight. Dark energy is not just an astronomical curiosity. It is a fundamental crisis in physics. The theory of quantum mechanics predicts that empty space, the vacuum, has energy. Quantum fluctuations, tiny, spontaneous appearances and disappearances of particles, give empty space a non-zero energy density. The calculation gives a specific number, and when astronomers measure the dark energy density of the universe, the energy responsible for the accelerating expansion, they get a different number, smaller, by a factor of approximately 10, 120, one followed by 120 zeros, smaller than the prediction. This is the largest discrepancy between theory and observation in the history of science. The theory predicts something 10, 120 times too large, and we do not know why. There is no agreement on how to resolve this, no leading candidate explanation, just the recognition that something fundamental about quantum mechanics, or about gravity, or about the nature of the vacuum is wrong, or missing, or not yet understood. What is dark matter? We have discussed this too. But let me say one thing I find particularly remarkable. We are confident dark matter exists. The evidence is overwhelming from multiple independent methods, but we have been searching for it directly, trying to detect a dark matter particle in the laboratory for over 30 years with increasingly sensitive instruments and found nothing. Not a signal, not a hint. The most common form of matter in the universe, passing through us right now, and we cannot catch it. That silence, the absence of a signal after 3 decades of increasingly sensitive searching, is one of the most important null results in the history of physics. It tells us that dark matter, whatever it is different from our best guesses, different from the simplest, most natural particle candidates. Something stranger, something we haven't thought of yet, or something that is simply very, very difficult to detect. Why is there more matter than antimatter? In the Big Bang, matter and antimatter were created in equal amounts. Equal, a particle for every antiparticle. When matter meets antimatter, they annihilate, converting entirely into energy. Equal amounts of matter and antimatter should have annihilated completely, leaving a universe of pure energy. No atoms, no stars, no planets, no us. But here we are, made of matter, in a universe of matter, which means that somehow the perfect symmetry between matter and antimatter was broken. Somehow, very early in the universe's history, a tiny excess of matter over antimatter was produced. For every 10 billion antiparticles, there were 10 billion and one particles. And when they annihilated, that one extra particle survived and became everything. The physical process that produced this asymmetry called baryogenesis is not known. We know it must have happened. We know roughly what conditions it required. But the specific mechanism, the physics that broke the symmetry, has not been identified. All the matter in the universe, every atom of every planet, of every star, of every galaxy exists because of a tiny asymmetry whose cause we do not know. Why does time move in only one direction? The laws of physics are, with a few exceptions, time symmetric. The equations of classical mechanics work the same whether time runs forward or backward. The equations of quantum mechanics work the same. The equations of electromagnetism work the same. Gravity works the same. If you filmed the collision between two billiard balls and played the film backward, it would look like a plausible physics problem. And yet, time clearly has a direction. The past is fixed. The future is open. You cannot unscramble an egg. You cannot unfold a burned building. Entropy always increases. Disorder always grows. The second law of thermodynamics, the source of time's arrow. But the second law is statistical, not absolute. It describes what is overwhelmingly likely, not what is absolutely required. And it explains the direction of time in terms of the growth of disorder. But it doesn't explain why the universe started in a highly ordered state, why the Big Bang was a state of extremely low entropy, extremely high order, from which everything since has been a relaxation, a slow spread into disorder. The ultimate origin of time's arrow, why the universe began in low entropy rather than high entropy, is not understood. What happened before the Big Bang? The Big Bang is our best model of the origin of the observable universe. 13.8 billion years ago, an extraordinarily hot, dense state, expanding, cooling, producing the hydrogen and helium that formed the first stars. But what came before, the question itself may not be well posed. Time, as we understand it, may have begun at the Big Bang. Asking what happened before may be like asking what is north of the North Pole. The question is grammatically correct but physically meaningless, but that is not satisfying. And several alternatives are seriously considered. Eternal inflation. The Big Bang was a bubble of low energy space forming in an eternally inflating background. Our universe is one bubble. There may be infinitely many others. Cyclic models. The Big Bang was a bounce. A previous universe collapsed to a minimum size and rebounded. Before our Big Bang, there was another universe. String theory landscapes. Our universe is one vacuum state in an enormous landscape of possible states. The Big Bang was a transition from one state to another. These are speculative, possibly untestable. The honest answer to what happened before the Big Bang is, we don't know. We may never know. And we aren't sure the question is a meaningful answer. Is the universe fine-tuned for life? The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, the cosmological constant have specific values, and it appears that if those values were even slightly different, the universe would be very different. A slightly stronger gravity. Stars burn out too quickly for life to develop. A slightly weaker gravity. Stars never form. A slightly different electron mass. Atoms don't form the right chemical bonds. A slightly larger cosmological constant. The universe expands too quickly for galaxies to form. The universe appears fine-tuned. The constants appear to be set in the narrow range that permits stars, planets, chemistry, and life. Why? 3 possible explanations. God. The constants were set by a creator who wanted life. The multiverse. There are many universes with different constants. We live in one where the constants are right for life, because we could only exist in such a universe. Necessity. The constants couldn't have been different. Future physics will show that these values are the only consistent ones. Science cannot adjudicate between these explanations. The fine-tuning problem is one of the most profound questions in physics and philosophy, and it is not resolved. What is the nature of quantum entanglement? 2 particles can become entangled. Their quantum states become correlated, so that measuring one particle instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. He didn't like it. He thought it meant quantum mechanics was incomplete, that there were hidden variables that determined the outcomes of measurements, and the apparent spookiness was just our ignorance of those variables. In 1964, physicist John Bell derived a theorem that showed how to test this, and the experiments, dozens of them, increasingly precise, have consistently shown that Einstein was wrong. The correlations between entangled particles are too strong to be explained by hidden variables. Quantum mechanics is not hiding a simpler, local, deterministic theory underneath. The entanglement is real, but what it means, what the physical reality is that produces these correlations, is deeply contested. Different interpretations of quantum mechanics give different answers, and there is no consensus on which interpretation is correct, or even on what experiment would distinguish between them. What is the measurement problem in quantum mechanics? In quantum mechanics, a particle exists in a superposition of states, both spin up and spin down, both here and there, until it is measured, at which point, according to the standard formulation, the wave function collapses. The particle is found to be in one state. The superposition disappears. The many become one. But what is measurement? What triggers the collapse? When exactly does it happen? Why does measurement and interaction between a particle and the detector have this special status? Why does the act of observation change the state of the system? Different interpretations of quantum mechanics answer these questions differently. The Copenhagen interpretation: the wave function is not a real physical thing, just a mathematical tool for predicting probabilities. The collapse is not a physical event. The many worlds interpretation: the wave function never collapses, all outcomes happen, the universe branches, we are in one branch. The objective collapse theories: the wave function is real and does collapse, but the collapse is a physical process that happens spontaneously, not through measurement. The pilot wave interpretation: particles have definite positions at all times. They are guided by a pilot wave that determines their behavior. These interpretations make different claims about physical reality, and there is no consensus, no experiment that has definitively distinguished between them. The foundation of the most accurate theory in physics, quantum mechanics, is a matter of active philosophical debate. After 100 years, why is gravity so weak compared to other forces? Gravity is the weakest force in nature by an enormous margin. The electromagnetic force is roughly 1036 times stronger than gravity at the scale of atomic particles. 36 orders of magnitude. You can hold a refrigerator magnet to your refrigerator and it will resist the gravity of the entire Earth. The magnet is winning against the planet. That is how weak gravity is. But gravity is long range and always attractive. So at large scales, at the scale of planets and stars and galaxies, it dominates. But why is it so weak? Why is there this enormous hierarchy between the strengths of forces? Physicists call this the hierarchy problem. It is one of the great unsolved problems of fundamental physics. Supersymmetry, a proposed extension of the Standard Model, was developed partly to address this problem, and the Large Hadron Collider was built partly to look for the supersymmetric particles that should have resolved it. So far, no supersymmetric particles. The hierarchy problem remains unsolved. What is space made of? Empty space. What is it? Intuitively, it seems like nothing, the absence of things. But modern physics does not allow truly empty space. The quantum vacuum, the lowest energy state of space, seethes with virtual particles, temporary fluctuations, pairs of particles and antiparticles appearing and disappearing. Space has energy. Space has structure. Space can be curved by mass and energy, according to general relativity. Space can expand. Space can carry waves, gravitational waves, propagating perturbations of space-time itself. So space is not nothing. But what is it? What is the physical stuff of space? What is space-time made of at the most fundamental level? This is one of the deepest questions in physics. String theory proposes that space emerges from the interactions of strings. Loop quantum gravity proposes that space is made of discrete atoms, quanta of space. Other approaches suggest that space and time are not fundamental but emergent, that they arise from something deeper, something we don't yet have the concepts to describe. What space is made of is not known. The mysteries of the Earth, what our own planet still hides, what causes ice ages. The Earth has experienced many ice ages, periods when large ice sheets covered much of the northern hemisphere, extending as far south as what is now New York City, London, Moscow. The last ice age ended about 11,700 years ago. The glacial interglacial cycles, the rhythm of ice ages and warm periods, follow a rough pattern. About 100,000 years for the full cycle in the more recent past. About 41,000 years earlier, The Milankovitch cycles, variations in the Earth's orbit and axial tilt, provide a forcing mechanism, a rhythm of increased and decreased solar radiation at different latitudes, and the climate response. But the correspondence between Milankovitch forcing and ice age timing is imperfect. The transitions are sharper than the forcing. The 100,000-year cycle is dominant in the recent record, even though the Milankovitch forcing at that frequency is weak. Something is amplifying the forcing. Feedback mechanisms. The growth of ice sheets increases the Earth's albedo, its reflectivity, cooling the planet further. The ocean circulation changes. The carbon cycle changes. But the precise mechanism by which relatively small orbital changes trigger and end ice ages, the sequence of feedbacks and thresholds that produces the dramatic transitions, is not fully understood. We know what drives the rhythm. We don't fully understand the music. What is the origin of Earth's water? Earth's surface is 71% water. About 1.386 billion cubic kilometers of it. The oceans. Where did it come from? The early Earth was very hot, formed by the violent collisions of asteroids and planetesimals. Any water on the surface should have evaporated and been lost to space. So the water must have arrived later. Two main hypotheses. Comets. Comets are rich in water ice. Bombardment of the early Earth by comets could have delivered the water. Asteroids. Certain asteroids, C-type asteroids, carbonaceous chondrites, contain significant amounts of water-bearing minerals. Asteroid bombardment could have delivered the water. The isotopic signature of Earth's water, the ratio of regular hydrogen to deuterium, is closer to asteroids than to comets. This suggests asteroids were the primary source, but the evidence is not conclusive. The origin of Earth's oceans, one of the most fundamental features of our planet, is not definitively established. What causes the Earth's magnetic field to reverse? The Earth's magnetic field reverses. The north and south magnetic poles switch places, not constantly, but periodically, on timescales of hundreds of thousands to millions of years. It has happened hundreds of times in Earth's history. The last reversal, the Brunhes-Matuyama reversal, happened about 780,000 years ago. The reversals are recorded in the ocean floor. As new seafloor forms at mid-ocean ridges and cools, it records the direction of the magnetic field at that moment, creating stripes of alternating magnetic polarity on either side of the ridge. A record of every reversal for hundreds of millions of years. But what triggers a reversal? The magnetic field is generated by convective motions in the liquid outer core, electrical currents in the liquid iron and nickel. The dynamics of this system, governed by magnetohydrodynamics, are extraordinarily complex. Computer simulations can produce reversals, but the conditions that trigger reversal in the actual Earth, rather than in a simulation, are not understood. The current weakening of the magnetic field, which has been observed for several hundred years, may be a precursor to a reversal or a temporary fluctuation. We cannot tell what is in the Earth's inner core. The inner core of the Earth is a solid sphere approximately 1,220 kilometers in radius, approximately the size of the Moon, at the very center of the planet. We know it exists. We know its approximate size and position. We know it is solid because seismic waves that can only travel through solid material propagate through it. We know it is mostly iron, very hot, very dense. But the details, the exact composition, the crystal structure of the iron, the behavior of iron under those conditions of temperature and pressure are not fully known, because we cannot get there. No instrument has ever been near the inner core. The deepest borehole ever drilled reached 12 kilometers. The inner core is 5,100 kilometers away. We know the inner core through seismic waves, through the echoes of earthquakes traveling through the planet, and the picture assembled from those echoes is still incomplete. There is a region, an inner core, within the inner core, with different seismic properties. What it is, why it's different, what happened to create it unknown, what causes earthquakes at unexpected locations. Tectonic theory explains most earthquakes. The movement of tectonic plates, the friction at faults, the sudden release of stored elastic energy, the pattern of seismicity matches the plate boundaries remarkably well. But there are earthquakes that don't fit. Intraplate earthquakes, earthquakes in the middle of tectonic plates, far from any plate boundary, far from any obvious fault. The New Madrid seismic zone in the central United States. The Charleston, South Carolina earthquake of 1,886. The 2011 Virginia earthquake. What causes these? Some involve ancient buried faults reactivated by subtle stresses. Some may be triggered by the weight of sediment. Some may be related to the rebound of the Earth's crust after the removal of glacial ice thousands of years ago. But the detailed mechanism and the ability to predict which areas are at risk from intraplate earthquakes is not fully developed. We don't know where the next New Madrid earthquake will strike, or what controls the weather. Weather prediction has improved enormously. We can now forecast several days ahead with reasonable accuracy, and the accuracy continues to improve, but fundamental limits remain. The atmosphere is a chaotic system. Small perturbations amplify the famous butterfly effect, the flapping of a butterfly's wings in Brazil, affecting a tornado in Texas. Not because the butterfly's wings actually caused the tornado, but as a metaphor for the sensitivity of chaotic systems to initial conditions, small errors in measuring the current state of the atmosphere grow exponentially. Even with perfect physics, even with perfect computational power, there is a fundamental limit to how far ahead weather can be predicted, perhaps 2 to 3 weeks. Beyond that, the atmosphere is too chaotic, too sensitive, too complex. The exact limit and the physics that sets it is an active area of research. What drives ocean circulation? The global ocean circulation, the thermohaline circulation, the ocean conveyor belt moves water around the globe over a period of about 1,000 years. It distributes heat. It affects climate. It influences the carbon cycle. It affects marine ecosystems. We understand its broad features, but the mechanisms that drive it, the balance of forces, and especially its stability, are not fully understood. Is the thermohaline circulation stable, or can it be disrupted? Abrupt climate changes in the geological record, the Younger Dryas, for example, a sudden return to glacial conditions 12,900 years ago may have been triggered by disruptions to the ocean circulation. Is that happening today? The Atlantic meridional overturning circulation is weakening. We know this. But whether it will weaken gradually or rapidly or cross a tipping point and collapse, that is not known. The ocean is one of the most important climate regulators on Earth, and its future behavior is uncertain. Why do volcanoes behave differently? Some volcanoes erupt gently, producing lava flows that move slowly enough to walk away from. Others explode cataclysmically, producing pyroclastic flows that travel at hundreds of kilometers per hour. eruption columns tens of kilometers high, ash blanketing continents. What determines the style of an eruption, the composition and viscosity of the magma, the amount of dissolved gas, the geometry of the volcanic plumbing system, the rate of magma ascent. These factors interact in complex ways. And predicting whether a volcano will erupt gently or explosively or at all is one of the central challenges of volcanology. We have made progress. We can monitor volcanoes, detect the seismic signals of magma movement, measure ground deformation, detect changes in gas emissions, and issue warnings. But the physics of volcanic eruptions, especially explosive eruptions, is not fully understood. The surprise still happens. Volcanoes erupt without warning or produce eruptions far larger than expected, or fail to erupt despite what appear to be imminent signs. The Earth keeps its secrets, the mysteries of mathematics, what numbers cannot solve. Is the Riemann hypothesis true? This requires some background. The Riemann zeta function is a mathematical function. It takes a complex number and returns a complex number. The Riemann hypothesis, proposed by Bernard Riemann in 1859, states that all the non-trivial zeros of the zeta function lie on a specific line in the complex plane, the critical line where the real part equals 1/2. This sounds abstract, but the zeros of the Riemann zeta function are intimately connected to the distribution of prime numbers. The primes 2, 3, 5, 7, 11, 13 are the atoms of arithmetic. Every integer can be factored into primes. Their distribution among the integers is deeply connected to the zeta function. And if the Riemann hypothesis is true, we can make precise statements about that distribution, about where primes fall, about gaps between primes, about the statistical structure of numbers. The hypothesis has been checked for the first 10 trillion zeros, all on the critical line, but checked is not proved. A proof or a disproof, a single zero off the line has not been found. After 165 years, and it is one of the Millennium Prize problems, $1 million for a proof unclaimed. Does P equal no problem? This is the most important unsolved problem in computer science. P is the class of problems that computers can solve efficiently in polynomial time. Problems where the time to solve scales as a polynomial function of the size of the input. No problem is the class of problems for which a proposed solution can be verified efficiently. But finding the solution might require exponential time that grows exponentially with the input size. The question, is P equal to no problem? Can every problem whose solution can be quickly verified also be quickly solved? This matters enormously. Most cryptography depends on P not equaling no problem. The security of online banking, of encrypted messages, of passwords, all rely on the assumption that certain problems are easy to verify but hard to solve. If P equals no problem, all of this security collapses. Encryption becomes trivially breakable. If P does not equal no problem, as most computer scientists believe, then there's a fundamental limit. Some problems are genuinely hard to solve, even if they are easy to check. But no one has proved it in either direction. After 50 years of the most intense mathematical effort, what is the nature of mathematical truth? This is more philosophical than the others, but it is genuinely unresolved. Mathematics produces results of extraordinary certainty. A proof theorem is not just probably true or very likely true, it is necessarily true. True in every possible universe in which the axioms hold. And yet, Gödel's incompleteness theorems, proved in 1931, show that any consistent mathematical system powerful enough to describe arithmetic contains statements that are true but cannot be proved within that system. Not unprovable because they are false. Unprovable because the system is not strong enough to prove them. True but unprovable. What does this mean about mathematical truth? Is mathematics discovered or invented? Is mathematical truth objective, existing independently of minds, or is it a product of human thought? Is the reason mathematics describes the physical world so well a deep metaphysical fact that reality is fundamentally mathematical, or a coincidence of our evolved ability to perceive patterns? These questions are at the intersection of mathematics, physics, and philosophy, and they are not answered. The mysteries of evolution, what natural selection leaves unexplained, how did complex features evolve? Evolution by natural selection is extraordinarily well supported. The evidence is overwhelming, from fossils, from genetics, from direct observation of evolution in real time, but explaining the origin of specific complex features remains challenging. The eye, Darwin himself was troubled by this. To suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances, for admitting different amounts of light, and for the correction of spherical and chromatic aberration, could have been formed by natural selection, seems, I freely confess, absurd in the highest possible degree. He then went on to argue correctly that it is not absurd, that eyes evolved from simpler light-sensitive patches, that every intermediate stage was functional, that their complexity accumulated, but the detailed genetic and developmental pathway, the specific mutations and their order, the selective pressures at each step for even moderately complex features is often not known. We have the principle, we are still filling in the history. What is the evolutionary origin of altruism? Evolution favors traits that increase reproductive success. Why would an organism sacrifice its own reproductive success for another? Why would a soldier die in battle? Why would a stranger donate a kidney? Why would a person spend years caring for a sick friend? Kin selection, William Hamilton's theory, explains altruism toward relatives. Genes shared with relatives benefit from helping those relatives. Inclusive fitness, reciprocal altruism. Robert Triver's theory explains altruism toward non-relatives. You scratch my back, I'll scratch yours. If the helped individual is likely to reciprocate, helping is evolutionarily beneficial. These theories explain a lot, but they don't fully explain the extreme altruism humans show towards strangers. People who have no hope of reciprocation, who share no genes. Why? Cultural evolution, group selection, morality is a byproduct of other adaptations. The evolutionary origin of human morality, of the genuinely unselfish behavior humans are capable of, is not fully explained. Why do organisms have the number of chromosomes they do? Humans have 46 chromosomes, arranged in 23 pairs. Chimpanzees, our closest relatives, have 48. Dos haotiu helfiets. Goldfish have 100. Ferns can have over 1,000. The number of chromosomes does not track with the complexity of the organism or the amount of DNA. Why does each species have the number of chromosomes it has? And how does this evolve? Two chromosomes can fuse. This apparently happened in human evolution when two ancestral chromosomes fused to create human chromosome 2. Chromosomes can duplicate, they can split, but the specific factors that determine the stable chromosome number for a species and the evolutionary dynamics of chromosome rearrangement are not fully understood. What determines the lifespan of species? Some species live for days. Mayflies live as adults for a few hours. Others live for centuries. Greenland sharks, recently discovered to live up to 400 years. The Aldabra giant tortoise, over 200 years. Bowhead whales, over 200 years. The immortal jellyfish Turritopsis dohrnii can theoretically cycle through its life stages indefinitely. What determines lifespan? The evolutionary theory of aging, antagonistic pleiotropy, the disposable soma theory, provides a framework. Natural selection favors genes that benefit reproduction early in life, even if they are harmful late in life, because most animals in the wild don't live long enough for late life costs to matter. This predicts that organisms with high adult mortality rates, predation, disease should evolve short lifespans, and organisms with low adult mortality should evolve long lifespans. The theory fits many cases, but not all. And the molecular mechanisms that set the specific lifespan, the precise biological processes that cause a Greenland shark to live 400 years and a mouse to live 2, are not fully understood. The mysteries of the cosmos, what the universe does that we cannot follow, what are fast radio bursts? In 2007, astronomers analyzing archival data from a radio telescope discovered a strange signal, a brief milliseconds long burst of radio waves from outside the Milky Way, extraordinarily bright, but lasting only a fraction of a second. More radio bursts were detected from all directions in the sky, mostly extragalactic, some repeating, some appearing only once. The source of fast radio bursts was a complete mystery. Dozens of theories were proposed: merging neutron stars, magnetars, supernovae, alien civilizations. In 2020, a fast radio burst was detected from within the Milky Way. From a magnetar, a highly magnetized neutron star. This confirmed that at least some fast radio bursts come from magnetars. But at least some is not all. The variety of fast radio burst properties suggest multiple source types. Not all fast radio bursts have been explained. Some remain mysterious. What are the ultra-high energy cosmic rays? Cosmic rays are energetic particles, mostly protons, that travel through space at nearly the speed of light and strike Earth's atmosphere. Most cosmic rays have modest energies, but occasionally, rarely, a cosmic ray arrives with extraordinary energy, far more energy than anything produced by human particle accelerators. The most energetic cosmic ray ever detected, the Oh My God particle, detected in 1990. One had an energy of about 3 × 10^20 electron volts. That is roughly equivalent to a tennis ball thrown at 150 kilometers per hour. In a single proton, where do these particles come from? What accelerates them to such energies? Active galactic nuclei, gamma ray bursts, magnetars. The sources of ultra-high energy cosmic rays, the most energetic particles in the universe, are not identified. What is inside a black hole? We know what happens at a black hole's boundary, the event horizon, the region beyond which nothing, not even light, can escape. But what happens inside? General relativity predicts a singularity, a point of infinite density. But physicists believe a singularity indicates not a physical reality, but a breakdown of the theory. General relativity fails inside the black hole. Quantum mechanics must become relevant, but we don't have a theory of quantum gravity, a theory that combines quantum mechanics and general relativity. So we literally don't have the equations to describe what happens inside a black hole. Various proposals exist. The interior is replaced by a quantum foam, a Planck star, a state of matter at quantum gravitational density from which the black hole eventually bounces back. A fuzzball, a string theory object with no interior at all. None of these is established. What happens inside a black hole is unknown, possibly unknowable. Since information from inside cannot reach us outside the event horizon, do other universes exist? The multiverse? We have discussed this before, but let me say something about why it matters scientifically, not just philosophically. The fine-tuning problem, the apparent coincidence that the constants of physics have, the values that permit life, is much less mysterious in a multiverse. If there are many universes with different constants, we necessarily find ourselves in one where the constants are right for our existence. The fine-tuning is not a coincidence because we have selected anthropically a universe that permits our selection, but the multiverse is not testable. Not yet. Perhaps ever. It may be a permanent feature of our cosmology, a well-motivated theoretical idea that can never be confirmed, making it not quite science in the strict sense, and yet, some multiverse models make predictions that are in principle testable. Collisions between bubble universes would leave observable imprints in the CMB. We have looked, we haven't found them, which constrains but does not rule out certain multiverse models. The existence of other universes is the most fundamental question in cosmology, and it may be beyond the reach of observation. Forever, what is the ultimate fate of the universe? We think we know the broad outlines. Dark energy drives accelerating expansion. Galaxies outside the local group recede beyond the horizon. Stars burn out. Black holes dominate. Eventually, Hawking radiation evaporates the black holes. The universe enters the dark era, cold, dark, featureless, for an unimaginably long time. But is this the end? Some theories suggest the dark energy is not constant, that it could decay or reverse. A big rip, where the expansion accelerates so fast it tears apart galaxies, then solar systems, then atoms, then even subatomic particles. A big crunch if dark energy reverses and gravity wins, pulling everything back together. A big bounce, the collapse triggering another big bang. Or something else, entirely a phase transition of the vacuum itself. A vacuum decay, where a bubble of lower energy vacuum nucleates somewhere in the universe and expands at the speed of light, converting everything it touches to a new phase, ending everything. Instantly, without warning, the ultimate fate of the universe is not known. The current evidence points to a cold, dark, slow end, but the evidence is incomplete, and the universe may have surprises. The mysteries of biology, what life does that we cannot follow? How do trees communicate? We discussed this in an earlier episode, the fungal networks through which trees exchange nutrients and chemical signals. But the details are more mysterious than the headline. How do trees recognize which seedlings are their own offspring? Mother trees appear to favor their own offspring in the distribution of carbon through fungal networks. But how do they recognize them? There is no obvious mechanism, no nervous system, no memory in the sense we understand. And yet the selectivity exists. The experiments show it, the bias toward offspring, the sending of resources to the related rather than the unrelated. How? We don't know. How do cells divide with such precision? Every cell division is an extraordinary choreography. The DNA is duplicated. The duplicated chromosomes are separated. One complete set goes to each daughter cell. The cell pinches in two. Two identical daughters, each with a complete genome. The process involves hundreds of proteins working together with extraordinary precision. Errors happen, but rarely. Fewer than one error per 10 billion base pairs replicated. Less than one mistake per complete human genome copied. How is this precision achieved? What checks and balances ensure the accuracy? Some are known: proofreading enzymes that check the newly synthesized DNA, mismatch repair systems that correct errors that get through. But the full system, the coordination of hundreds of proteins, the timing, the spatial organization is not completely understood. The most reliable copy process in the known universe, and we don't fully understand how it works. What are the limits of regeneration? Some animals can regenerate lost body parts. Axolotls, Mexican salamanders, can regenerate entire limbs, complete limbs, bones, muscles, nerves, blood vessels, in weeks. From the stump, they can also regenerate parts of their hearts, parts of their spinal cords, parts of their eyes. Planarian flatworms can regenerate from a fragment. Cut a planarian into 280 pieces. Each piece grows into a complete worm. The head end knows to grow a tail. The tail end knows to grow a head. How do the cells know? How does positional information persist? How is the complete body plan reconstructed from a fragment? Humans cannot regenerate limbs, but we can regenerate our liver. If up to 70% of the liver is removed, it regrows to the correct size, not too large, not too small. What determines when to stop? What tells the regenerating organ that it has reached the right size? The molecular mechanisms of regeneration and the question of why some animals can regenerate and others cannot are not fully understood. How does the body know its own size? Related to regeneration but separate. Every organ in the body is the right size. The heart is not too large or too small. The liver fills the right space. The bones are the right length. Development produces the right size. And if an organ is damaged, the repair process stops at the right point. The liver stops regenerating when it has reached the right size. The skin stops healing when the wound is closed. How does a tissue know when it has grown enough? What is the signal? Organ size control the molecular mechanisms by which organs know their correct size and stop growing when they reach it is an active research area with significant implications for cancer. Cancer, in part, is the failure of size control. Cells that don't receive the stop signal or that ignore it and keep growing. Understanding how normal cells know when to stop may help us understand why cancer cells don't. What determines whether a species goes extinct? Some species survive mass extinctions, others don't. What predicts survival? Body size matters. Small animals generally survive mass extinctions better than large ones. Geographical range matters. Widespread species are more resilient than narrow endemics. Dietary flexibility matters. Generalists survive better than specialists. But these are patterns, not predictions. In the Permian extinction, the great dying species with traits that seemed adaptive were wiped out. Species with seemingly poor prospects survived. The survivors of major extinction events are not always the ones you would predict in advance, which suggests that chance, catastrophic, unpredictable, random chance, plays a large role. The specific trajectory of a mass extinction, which volcanoes erupt, which asteroid hits where, which diseases spread, is not determined by any property of the species. It is determined by history, by contingency, by the particular sequence of events. Whether a species survives a mass extinction depends largely on luck, being in the right place when the asteroid hit. Why do some genes have no known function? The human genome contains approximately 20,000 to 25,000 protein-coding genes. For decades, scientists assumed that most of the genome was functional, or that non-functional sequences were just junk. The ENCODE project, a massive effort to catalog the functional elements of the human genome, found that a large fraction of the genome is transcribed. That is, it is copied into RNA, but most of it doesn't code for protein. What does this RNA do? Some of it is known to have regulatory functions, small non-coding RNAs that regulate gene expression. Some of it is known to have structural functions, but much of it, a substantial fraction of the transcribed non-protein coding genome, has no known function. Whether it is functional or truly junk vestigial sequence with no current purpose is contested. This matters because it bears on how much of the genome is under selective pressure. How much is conserved by evolution because it does something important, and how much is neutral. The function of much of the genome is unknown. How do pathogens evolve to be more or less virulent? A pathogen that kills its host quickly cannot spread. So evolution should favor less virulent pathogens. But this isn't always what happens. The 1,918 influenza pandemic killed tens of millions of people. Ebola kills most of its victims. Rabies is almost always fatal. Why don't these pathogens evolve toward lower virulence? The answer depends on the mode of transmission. Pathogens that are transmitted before the host becomes too sick can afford high virulence. Pathogens that need the host to be mobile to transmit, like the common cold, evolve lower virulence. The specific evolutionary pressures and the speed with which pathogens evolve depend on many factors: transmission routes, host behavior, population density, immune responses, the evolution of virulence, the trajectory of a pathogen toward greater or lesser lethality cannot always be predicted. And the emergence of new pandemic pathogens like SARS-CoV-2 is not fully anticipated by existing theory. The evolutionary dynamics of infectious disease are not fully understood. The mysteries of human origins, where we came from and why we are different. When did language evolve? This is one of the most difficult questions in paleoanthropology. Language leaves no fossils. The soft tissues of the larynx and tongue essential for speech decompose. We cannot directly observe when our ancestors started speaking. We can infer from indirect evidence. The shape of the vocal tract reconstructible from skulls. The development of the hyoid bone, a small bone in the throat associated with speech. The size and complexity of the brain regions associated with language, the area around Broca's area, visible from the endocast of skulls. The genetic evidence, including the FOXP2 gene, a transcription factor important for language and speech, which is conserved across vertebrates but with human-specific mutations. Taken together, the evidence suggests that the capacity for language, the full modern version, evolved sometime in the last few 100,000 years. Perhaps 200,000 to 300,000 years ago, coinciding with the emergence of modern Homo sapiens. Perhaps more recently, 50,000 to 100,000 years ago, coinciding with the behavioral revolution visible in the archaeological record. The evidence is contested, the timing is debated, and the question of whether earlier species Homo erectus Neanderthals had language in any form is deeply uncertain. Why did Neanderthals go extinct? Neanderthals were not stupid. They had brains as large as ours, possibly larger. They made tools. They used fire. They buried their dead. They cared for the injured and elderly. Skeletons show evidence of individuals who survived serious injuries that would have required extended care. They may have made art. They may have used symbolic objects. They coexisted with modern humans in Europe for at least 2,600 years, and then they disappeared about 40,000 years ago. Why? We know modern humans and Neanderthals interbred. Modern humans outside Africa carry 1 to 4% Neanderthal DNA. So they did not simply compete. They met, they mated, they exchanged genes. But the Neanderthals as a distinct population disappeared. Climate change, competition for resources with modern humans, disease, modern humans carrying pathogens to which Neanderthals had no immunity, assimilation absorbed genetically into the modern human population. All have been proposed. None is established. The extinction of the Neanderthals, our closest evolutionary relatives, is not explained. What caused the Cambrian explosion? About 541 million years ago, almost all the major body plans of animals alive today appeared in the fossil record in a geologically brief period, perhaps 20 to 25 million years. The Cambrian explosion, before it, mostly simple, soft-bodied organisms. After it, a world of complexity, eyes, shells, legs, mouths with teeth, predation, defense, the ecological arms race. What triggered this explosion of biological diversity? Several hypotheses. The Great Oxidation Event, the rise of oxygen in the atmosphere and ocean, making the energy-intensive process of building complex bodies possible. The end of snowball Earth, the thawing of a globally glaciated planet, releasing nutrients into the ocean. Ecological cascades, the evolution of predation, creating selective pressure for defense, for shells, for speed. Genetic innovations, the evolution of the regulatory gene networks, Hox genes, that allow complex body plans to be specified and modified. All of these probably contributed, but which was the primary trigger? What made the Cambrian explosion happen when it did? Not clear. The origin of animal life as we know it remains a deep puzzle. The mysteries of matter, what things are made of at the deepest level. 61. Why are there 3 generations of fundamental particles? The standard model of particle physics describes the fundamental particles of nature, quarks and leptons, and the forces between them. Quarks come in 3 generations. Up and down quarks, first generation. Charm and strange quarks, second generation. Top and bottom quarks, third generation. Leptons come in 3 generations too. Electron, neutrino, first generation. Muon, neutrino, second generation. Tau, neutrino, third generation. Each generation is heavier than the previous. The second and third generation particles decay into first generation particles very quickly. In our everyday world, only first generation particles are stable. But the second and third generation particles exist. Why 3 generations? Why not 1? Why not 5? The Standard Model contains the 3 generations as a given. It does not explain why there are 3, or what, if anything, determines the number. This question, why there are exactly 3 generations of fundamental particles, is not answered by any current theory. Why do the constants of nature have the values they have? The fine structure constant alpha, approximately 1 over 137, the ratio of the electron charge squared to the product of the reduced Planck constant and the speed of light. It determines the strength of the electromagnetic interaction. Why is it 1 over 137 and not 1 over 100 or 1 over 1000? The physicist Richard Feynman called alpha one of the greatest damn mysteries of physics. He said every physicist should worry about it, that you could write a book about why it is 1 over 137 but not any other number. And the book would be blank because no one knows. The constants of nature, alpha, the gravitational constant, the masses of fundamental particles are inputs to the Standard Model. Parameters measured, not derived. No deeper theory explains why they have the values they have. This is one of the most profound puzzles in physics. Why does the universe have these particular constants? Why these numbers and not others? What is the proton radius? This seems like it should be easy. Measure the size of the proton. It has been measured many times by different methods, and the different methods give different answers. The proton radius puzzle emerged in 2010 when measurements using muonic hydrogen with a muon instead of an electron, gave a proton radius about 4% smaller than measurements using regular hydrogen. 4% doesn't sound like much, but it is many times the experimental uncertainty. The discrepancy is statistically significant. Why do the 2 methods give different answers? Do electrons and muons interact with the proton differently than expected? Is there new physics, a new force or particle that the Standard Model doesn't account for? Or is there a systematic error in one or both measurements? The proton radius puzzle has been the subject of intense research. Some measurements have recently converged, but the puzzle is not fully resolved. A disagreement about the size of the proton, which should be a settled question, but isn't. What is the structure of quark-gluon plasma? In the first microseconds after the Big Bang, the universe was so hot and dense that quarks and gluons, the constituents of protons and neutrons, existed freely, not bound inside hadrons. Free. This state of matter, quark-gluon plasma, was recreated in the laboratory. At the Large Hadron Collider at RHIC in Brookhaven, by colliding heavy ions at nearly the speed of light, creating for fractions of a second the hottest temperature ever achieved in a laboratory, hotter than the surface of the sun by factors of hundreds of thousands. And quark-gluon plasma does not behave the way physicists expected. They expected it to behave like a gas, a hot gas of quarks and gluons. Instead, it behaves like a liquid, almost a perfect fluid, with the lowest viscosity of any known substance. Why? What is the structure of quark-gluon plasma? Why is it so liquid-like? The physics of strongly interacting matter at extreme temperatures, the physics of quark-gluon plasma, is not fully understood. Why is the universe three-dimensional? We live in a universe with 3 spatial dimensions and 1 time dimension. Why 3? String theory requires 10 or 11 dimensions for consistency. Where are the others? The standard answer: the extra dimensions are compactified, curled up so small at scales near the Planck length that they are not observable. But this raises the question, why are three dimensions large and the others small? What physical process in the early universe caused three dimensions to expand while the others stayed tiny? And could it have been different? Are there universes in the multiverse with four large spatial dimensions? Or two? Would they be capable of harboring complex structure and life? Physicists have argued that planets with stable orbits around stars require exactly three large spatial dimensions. In more or fewer dimensions, orbits are unstable. This is an anthropic argument for why we observe three large dimensions. But the underlying physics, why the universe has three large spatial dimensions rather than some other number, is not explained. The mysteries of medicine, what we cannot heal. Why do people get cancer? We know a great deal about cancer. It is fundamentally a disease of uncontrolled cell division, caused by mutations in genes that regulate the cell cycle. Oncogenes, mutated genes that promote cell division. Tumor suppressor genes, mutated genes that no longer suppress cell division. Multiple mutations are required. Cancer is typically a multi-step process, accumulating over years or decades. We know risk factors: smoking, UV radiation, certain viruses, chemical exposures, genetic predisposition. We have treatments that work: surgery, chemotherapy, radiation, immunotherapy, targeted therapies. And yet, the fundamental question, why do some people with the same exposure get cancer and others don't, is not answered. Why do some cancers respond to treatment and others don't? Why do some cancers spread, metastasize, and others don't? The biology of metastasis, the process by which cancer cells leave the primary tumor, travel through the blood or lymph, and establish new tumors in distant organs, is not fully understood. And it is metastasis that kills, not the primary tumor. Cancer kills when it spreads. Understanding and preventing metastasis is one of the great challenges of medicine. What causes Alzheimer's disease? Alzheimer's disease is the most common form of dementia, affecting tens of millions of people worldwide. It is characterized by the accumulation of abnormal protein deposits in the brain. Amyloid plaques, deposits of the protein amyloid beta between neurons. Neurofibrillary tangles, accumulations of the protein tau inside neurons, and the progressive death of neurons. Loss of memory, loss of cognitive function, loss of personality. The amyloid hypothesis, the idea that amyloid beta accumulation is the primary cause of Alzheimer's, has dominated research for 3 decades. Many drugs have been developed to clear amyloid from the brain. Most clinical trials have failed. Some have shown modest benefits. But the drugs that successfully clear amyloid do not always improve cognition. This has led some researchers to question whether amyloid is the cause of Alzheimer's or a symptom, whether the disease is amyloid-driven or whether amyloid is a downstream consequence of something else. In 2022, a major research fraud was discovered in foundational Alzheimer's research. Key papers were found to contain manipulated images. This has further complicated the picture. The cause of Alzheimer's disease, the primary driver of the neurodegeneration, is not known. What causes autoimmune diseases? Rheumatoid arthritis, multiple sclerosis, type 1 diabetes, lupus, Crohn's disease, celiac disease. In all of these, the immune system attacks the body's own tissues. Why? Genetics plays a role. Specific HLA variants increase risk. Environmental triggers play a role. Certain infections may trigger autoimmunity. The gut microbiome plays a role. The composition of gut bacteria influences immune development and function. Hygiene may play a role. The hygiene hypothesis suggests that reduced exposure to pathogens in early childhood leads to an immune system that is more likely to malfunction. But the causal chain, the specific sequence of events that leads from genetic predisposition and environmental exposure to immune system attacking self, is not established for any autoimmune disease. And the increasing prevalence of autoimmune diseases in industrialized countries, a trend of the last 50 to 100 years, is not explained. Something has changed in the environment, in the diet, in the microbiome. We don't know what. How does the placebo effect work? If you give a patient a sugar pill and tell them it is an effective painkiller, their pain often decreases. If you tell a patient that surgery was performed when in fact no surgery was done, they often report improvement in the condition the surgery was supposed to treat. The placebo effect is real, measurable, significant. It is not just in the mind, in the dismissive sense. It produces real physiological changes. Neuroimaging shows that placebo treatment for pain activates the same brain regions as real analgesics. Endogenous opioids are released. The effect is mediated by real biochemistry. But how? How does the belief that treatment has occurred produce real physiological changes? How does expectation alter the activity of neurons, the release of neurotransmitters, the function of the immune system? The placebo effect reveals a profound connection between belief, mental state, and physical function, a connection whose mechanism is not understood, and whose implications for medicine, for the mind-body relationship, for the nature of healing are not fully appreciated. What causes chronic pain? Acute pain, the pain from a cut or a broken bone, is well understood. It is a signal damage has occurred. The nervous system is alerting the brain. Protect this area, avoid further damage. But chronic pain, pain that persists for months or years after the original injury is healed, is much more mysterious. The signal is still firing, but there is nothing to signal. The tissue has healed, the damage is gone, and yet the pain persists. Why? The nervous system is changed, sensitized. Central sensitization, changes in the spinal cord and brain that lower the threshold for pain signals, is a real phenomenon. But why it develops in some people and not others? Why some injuries lead to chronic pain and most do not? What the molecular and cellular changes are, how to reverse them. These questions are not answered. Chronic pain affects hundreds of millions of people. It is the leading cause of disability worldwide, and we don't fully understand why it happens, the mysteries of society, what humans do together that we cannot predict, what causes wars, not the proximate causes, the assassination, the border dispute, the colonial rivalry, the deep causes. Why do humans who are capable of extraordinary cooperation and compassion also wage organized violence on each other? Is aggression innate, evolutionary, a product of competition for resources, or is it cultural, learned, a consequence of specific political and social structures? Steven Pinker, in his book The Better Angels of Our Nature, argues that violence has declined over historical time, that the world is becoming less violent. The data, he argues, support this. Others contest this, argue that Pinker's data are selective, that the measurement of violence is not straightforward, that the decline, if real, is contingent and fragile. The causes of war, the conditions under which humans choose organized violence over negotiation, are studied by political scientists, economists, historians, psychologists, biologists, without consensus. The prediction of specific conflicts is essentially impossible. The prevention of war, the conditions that reliably produce peace, is imperfectly understood. What determines economic growth? Why are some countries wealthy and others poor? This seems like it should have an answer, and many answers have been proposed. Geography, access to resources, to navigable waterways, to temperate climates, institutions, property rights, rule of law, democratic governance, culture, values and behaviors that promote investment, education, cooperation, technology, the adoption and development of productive technologies, historical contingency, the legacy of colonialism, of specific political events. All of these correlate with economic development. None of them fully explains it. The correlation between institutions and growth is strong. But which comes first? Do good institutions produce growth, or does growth produce good institutions? The causal arrows are hard to establish, and the policies that reliably produce growth in poor countries, the conditions that allow the kind of economic transformation that turned South Korea and Taiwan from poor countries to wealthy ones in a generation, clearly identified. Development economics, the field that studies these questions, has undergone multiple paradigm shifts. And the fundamental question of why some societies prosper and others do not is not answered. What drives cultural change? Why did the Renaissance happen? Why did the scientific revolution emerge in Western Europe in the 17th century rather than in China, which was technologically more advanced? Why do fashions change? Why do moral norms evolve? Cultural evolution, the transmission and transformation of ideas, behaviors, and values across time, is studied by anthropologists, historians, sociologists, evolutionary biologists. Models of cultural evolution analogous to genetic evolution have been developed. Cultural transmission, variation, selection. But cultural evolution is vastly more complex than genetic evolution. Ideas can spread horizontally from person to person who are not parent and child. Ideas can change dramatically in transmission. Ideas interact with each other in complex ways. The history of human culture is full of surprises, of ideas that spread rapidly and unexpectedly, of revolutions that no one predicted, of cultural practices that persisted unchanged for centuries and then vanished overnight. The dynamics of cultural change are not captured by current theoretical models. The future of culture cannot be predicted. The mysteries of perception, what the senses hide, why do humans have music? Every human culture has music. It appears to be universal, as fundamental to human experience as language, more ancient than written language. Musical instruments have been found in Paleolithic sites 40,000 years old. But the evolutionary origin of music is deeply puzzling. What is music for? Why did evolution produce the capacity for it? And the response to it, why does music make us feel things? Why can a sequence of sounds make us weep, or exhilarated, or nostalgic? Darwin thought music might be a form of sexual display like birdsong. Some researchers argue music evolved for mother-infant communication, a precursor to language used to communicate emotional states. Others argue it evolved as a mechanism for social bonding, synchronized movement, and vocalization, creating group cohesion. But none of these explanations fully accounts for what music actually does. The fact that music can express and induce specific emotions, that a minor key feels sad across cultures, That rhythm can entrain the body. That music can recall specific memories with extraordinary vividness. The psychology and neuroscience of music are rich areas of research without settled answers about why music exists and why it means what it means to us. Why do humans find things beautiful? Across cultures, certain things are found beautiful. Symmetrical faces, certaines proportions, certain landscapes, bright colors, clear water, open space with some trees, and certain things are found beautiful only within specific cultural contexts. Certain paintings, certain music, certain architecture, some beauty appears universal, some is culturally specific. Why? The evolutionary aesthetics hypothesis, we find things beautiful that were adapted for our ancestors. Symmetrical faces signal genetic health. Open landscapes with water and trees signal a good habitat. The evolutionary history of our species shape what we find beautiful. But this doesn't explain why a piece of music from 300 years ago by a composer in a different cultural context can move us to tears, or why abstract art with no obvious adaptive value is found beautiful, or why our sense of beauty evolves over our lifetime. The psychology of beauty, what we find beautiful, why and how, is not explained. How does smell produce memory? The smell of a specific food can transport you instantly, not gradually, instantly, to a specific moment. A kitchen in childhood, a person long gone, a place you have not thought of in decades. The smell triggers the memory with a vividness and immediacy that other senses rarely achieve. Why? The anatomy provides a clue. The olfactory bulb, the brain structure that processes smell, has a direct connection to the hippocampus and amygdala. The brain structures involved in memory formation and emotional processing are more direct connection than other senses, which travel through the thalamus first. Smell goes direct to the emotional memory center, but the exact mechanism why olfactory cues are so potent at triggering autobiographical memories is not fully explained. The Proustian memory, the involuntary rush of past experience triggered by a smell, is real, and its mechanism is only partly understood. What is the mechanism of taste? We have 5 basic tastes: sweet, salty, sour, bitter, umami. The receptors for some of them are known: the sweet receptor, the bitter receptor, the umami receptor, but the full picture is more complex. Taste perception varies enormously between people. Super tasters, who have more taste buds and taste more intensely, experience flavors very differently from non-tasters. The same food can taste radically different to different people. The integration of tastes, smell, texture, temperature, and expectation into what we call flavor is an extraordinarily complex perceptual process. And our preferences, why we like what we like, are shaped by genetics, experience, culture, and factors we don't fully understand. The neuroscience of taste, and especially the question of how taste preferences are formed and why they vary so much, is not fully worked out. The mysteries at the frontier, the questions being asked right now: what are the long-term consequences of microplastics? Microplastics are everywhere: in the ocean, in the air, in the soil, in the food we eat, in the water we drink, in the blood and tissues of living animals, including humans. Microplastics have been found in human blood, lungs, breast milk, placentas, colons, and brains. The health consequences are not known. Some laboratory studies show that high concentrations of microplastics can harm cells. But the concentrations in laboratory studies are often higher than current environmental exposures. What are the effects of chronic low-level exposure? Over a lifetime? We don't know. The generation now being born is the first to have been exposed to microplastics from conception. What will the cumulative exposure mean for their health? We don't know. We are running an uncontrolled experiment on every living thing on the planet, and we won't know the results for decades. How do ecosystems recover from disruption? Ecosystems can be resilient. After a volcanic eruption, the landscape is colonized. Life returns. The ecosystem rebuilds over decades or centuries, but ecosystems can also shift permanently to a different state. A lake that was clear can shift to a turbid, algae-dominated state and not shift back, even after the nutrient inputs that caused the shift are removed. The lake is in a different basin of attraction, a different stable state. Tipping points, regime shifts, critical transitions. These are real. They happen in lakes, in forests, in coral reefs, in fisheries. But predicting when an ecosystem is approaching a tipping point, when it is close to a regime shift, is one of the hardest problems in ecology. And the recovery of ecosystems from human disturbance, whether they will return to their previous state or shift to something else, cannot be reliably predicted. The future of the world's ecosystems is uncertain. What are the long-term consequences of sleep deprivation? We know that acute sleep deprivation is harmful. Impaired cognition, impaired immune function, impaired metabolic function. And chronic mild sleep deprivation, getting 6 hours instead of 8, has measurable effects on cognition and health. But the long-term consequences of the low-level chronic sleep deprivation that is endemic in modern industrialized societies are not fully understood. The association between short sleep and increased risk of Alzheimer's disease, possibly because the lymphatic system needs sufficient sleep time to clear metabolic waste, is concerning. The association between short sleep and increased risk of cardiovascular disease, obesity, diabetes, cancer. These associations are real, but the causal mechanisms are not fully established. And the question of whether the sleep deprivation of modern life is a public health crisis comparable to smoking, a widespread, preventable, serious health hazard, is not settled. The deep mysteries, the questions beyond questions. Is there objective meaning in the universe? This is not a scientific question, but it is a question that science cannot avoid. Science describes what is. It does not tell us what to value, why anything matters, whether anything matters, whether the universe has any inherent direction, any purpose, any meaning independent of the creatures within it who create meaning. Nihilism says no. The universe has no inherent meaning. Any meaning is human-made, borrowed, temporary. Religious traditions say yes. The universe was created with purpose, by a creator who cares. And meaning is not made but discovered. Existentialism occupies the middle ground. The universe has no inherent meaning, but humans are the kind of beings that must create meaning. And that creation is authentic, not merely borrowed. These are not empirically decidable questions. Science cannot tell us whether anything matters. And yet most of us live as if things matter, as if this conversation matters, as if the person next to you matters, as if the future matters. We act as if meaning exists, even without proof. Maybe that is all meaning is. the act of living as if it exists. Is the universe deterministic? Classical physics is deterministic. Given complete information about the current state of the universe, its future is in principle determined. Every future event is fixed. The laws are fixed. The initial conditions are fixed. The outcome is fixed. You chose nothing. Everything you think you chose was determined by the state of the universe when you were born. And the state when you were born was determined by what came before. All the way back to the Big Bang. Quantum mechanics complicates this. Quantum mechanics introduces genuine randomness, fundamental, irreducible randomness, not randomness that comes from ignorance, but randomness that is built into the structure of reality. The outcome of a quantum measurement is not determined. It is genuinely random, within probabilistic constraints. But does quantum randomness rescue free will? Replacing determinism with randomness doesn't obviously give us control. A decision determined by random quantum fluctuations is no more mine than a decision determined by prior causes. Free will, the sense that we are the authors of our choices, is not explained by either determinism or quantum randomness. The question of free will remains open in philosophy, in neuroscience, in physics, and in the quiet uncertainty of anyone who lies awake wondering whether they are choosing or whether they are being chosen. Why is there something rather than nothing? This is the oldest question, the deepest question. Why does anything exist? Not why is there this universe rather than some other, but why is there anything at all? Why not nothing? Eternal, absolute nothing. No space, no chimney, no laws, no mathematics, no possibility, just nothing. Leibniz asked it in 1714. Why is there something rather than nothing? He answered with God. But this doesn't resolve the question. It postpones it. Why does God exist rather than nothing? Physics answers, the universe came from a quantum fluctuation. Nothing is unstable. The quantum vacuum, empty space, seethes with virtual particles. It is energetically favorable for particles to exist. Nothing, true, absolute nothing, violates quantum mechanics. But this assumes quantum mechanics exists, assumes the laws of physics exist. Why do the laws of physics exist? Who or what specifies them? Why are they this way rather than some other way? Why is there a way at all? The question recurses. Every answer pushes the mystery back one step, and the step before that is still mysterious. Why is there something rather than nothing? The question that ends all questions, that has never been answered, that may not be answerable, that lives at the bottom of everything. What is the nature of numbers? Numbers are extraordinarily real. In some sense, the number 7 exists. It is not a physical object. You cannot touch it or weigh it or measure its temperature. But it is not nothing. It has properties. It is prime. It is odd. It is the square root of 49. It has relationships with other numbers that are fixed, independent of who knows them, independent of whether any mind has ever thought about them. The equation 7 plus 5 equals 12 was true before any mathematician ever wrote it, before any human existed, before the earth existed. Was it true before the universe existed? Is mathematical truth eternal, independent of physical reality? The Platonist says yes. Mathematical objects are real. They exist in an abstract realm. Mathematicians don't invent mathematics. They discover it. The nominalist says no. Numbers are human concepts, invented, useful, powerful. but ultimately a product of mind, not independent of mind. This is not a trivial philosophical debate. It bears on the question of why mathematics describes physical reality so well. If mathematics is invented, the effectiveness of mathematics and physics is a profound coincidence. If mathematics is discovered, if it has a reality independent of minds, then perhaps the universe is, in some deep sense, mathematical. And the correspondence between math and physics is not a coincidence, but a feature of reality. We do not know which is correct. The nature of mathematical truth is unsettled. Are there fundamental limits to human knowledge? Gödel showed there are limits to mathematical knowledge. Heisenberg showed there are limits to what can be simultaneously known about a particle. The cosmic horizon sets limits on what can be observed. Are there limits to what humans can ever know? There are things that cannot be observed. The interior of black holes, the universe beyond the cosmic horizon, the state of the universe before inflation. But are there things that cannot even be formulated? Things so far outside human cognitive categories that we cannot even ask the right questions about them? Our brains evolved in a specific environment to solve specific problems. There is no reason to think they are capable of understanding everything. A dog cannot understand calculus, not because it lacks the effort or the training, because its brain simply does not have the architecture. Are there aspects of reality that require cognitive architecture we don't have? Aspects of the universe that are simply beyond us, not unknown, unknowable, but us. This is possible. And the thought is, I find both humbling and strangely exciting, because it means there may be more to the universe than anything we will ever understand, more than the minds we have can hold, more than the questions we can ask. What is time, really? Not the direction of time, not why time flows from past to future, but what time is. Is time a dimension, a physical substance? Is it fundamental or emergent arising from something deeper? In general relativity, time is woven together with space into space-time. A four-dimensional fabric, curved by mass and energy, different for different observers. There is no universal now. What is simultaneous for you is not simultaneous for someone moving relative to you. Time is relative, personal, different at different points in space. In quantum mechanics, time plays a peculiar role. The Schrödinger equation treats time differently from space. And in attempts to quantize gravity, to build a theory of quantum gravity, time causes enormous difficulties. In some approaches to quantum gravity, time disappears entirely. It is not a fundamental feature of reality. It emerges from something deeper, from the correlations between quantum systems, from the growth of entanglement. The physics of time, what time actually is not settled, and may be one of the deepest puzzles in the foundations of physics. What is the relationship between information and physical reality? John Archibald Wheeler, one of the great physicists of the 20th century, proposed the phrase "it from bit." The idea that physical reality, the it, is fundamentally constituted by information, the bit. That the universe is, at some level, informational, not material, not energetics. Informational, this is not a fringe idea. It is taken seriously by physicists who work on quantum gravity and quantum information. The laws of black hole thermodynamics connect entropy information to the geometry of space-time. The holographic principle derived from string theory and black hole physics suggests that the information content of a volume of space is encoded on its boundary, that three-dimensional reality is, in some sense, a projection from a two-dimensional surface. If physical reality is fundamentally informational, if information is more basic than matter and energy, then what is information? Information about what? In what substrate does it reside? These questions are not answered, but they point toward a possible revolution in how we understand physical reality. As fundamental as the revolutions of quantum mechanics and relativity, does mathematical structure exist independently of minds? I asked this before about numbers, but let me make it broader. The equations of physics, Maxwell's equations, the Schrödinger equation, Einstein's field equations, describe reality with extraordinary precision. They were discovered, not invented. Mathematicians and physicists feel strongly that they are finding something real, not creating it. Max Tegmark, a cosmologist at MIT, has argued for the mathematical universe hypothesis, the idea that our universe is not merely described by mathematics. It is mathematics, a particular mathematical structure. Among all possible mathematical structures, if this is true, if the universe is a mathematical object, then everything that exists is, at its most fundamental level, abstract. Structure, relationship, pattern, without physical substance, without stuff, just mathematics all the way down. This is an extraordinary claim, and I don't know what to do with it. I find it alternately compelling and vertiginous. The question of whether mathematics is discovered or invented, whether the universe is made of stuff or made of structure, is not resolved. The final mysteries, questions that may never be answered. Are we alone in the universe? We have discussed the Fermi paradox, the silence, the mathematics that seem to demand life, and the sky that seems to say, we are alone. I want to add something here. The question is not just scientific, it is existential. If we are alone, if the Earth is the only living world in the observable universe, then life is inconceivably precious and inconceivably fragile. Everything that has ever lived, everything that has ever felt anything, everything that has ever been conscious, all of it here, on this one planet, in this one galaxy, in this one moment, the only flame in the dark. If we are not alone, if the universe is full of life, then the question of why we haven't found any becomes more urgent and more disturbing. Are there filters, great barriers that prevent civilizations from surviving? Is there something, some step in the development of technological civilization that is extraordinarily difficult or extraordinarily dangerous? We don't know which scenario is true. We don't know whether our aloneness is because we are rare or because something terrible awaits. What is the nature of the very small? The Standard Model describes elementary particles, the fundamental constituents of matter, quarks, leptons, Gauge bosons. Are these truly elementary, or do they have internal structure? Are they made of something smaller? The history of physics suggests that things thought to be elementary turn out not to be. Atoms were thought to be elementary. Then we found the nucleus. The nucleus was thought to be elementary. Then we found protons and neutrons. Protons and neutrons were thought to be elementary. Then we found quarks. Are quarks and leptons truly elementary? Or are they made of strings, of loops of space, of something we have not yet imagined? the question of what is truly fundamental, what is at the absolute bottom of physical reality, below which there is nothing smaller, may not have a bottom. It may recurse forever, or it may stop. At the scale we haven't reached, we don't know. What is the ultimate theory of physics, the standard model, the most accurate theory in physics, tested to extraordinary precision, but incomplete? It does not include gravity. It does not explain the masses of particles. It does not explain why there are 3 generations. It does not explain dark matter. It does not explain dark energy, general relativity, our theory of gravity, extraordinarily well tested at the scales where it has been tested, but incompatible with quantum mechanics at the smallest scales. A theory of everything, a theory that unifies quantum mechanics and gravity, that explains all particles and forces, that reduces all of physics to a single framework, is the holy grail of theoretical physics. Sought for a century, not found. String theory is the leading candidate with extraordinary mathematical beauty and no confirmed experimental predictions. Loop, quantum gravity is another approach, different mathematics, different assumptions, also without confirmed experimental predictions. The ultimate theory of physics, if one exists, is not known. It may not be knowable with our current tools. It may require instruments that don't exist. It may require ideas that haven't been thought yet. Can consciousness be explained without appealing to something non-physical? This is the hardest problem again, from a different angle. Every physical theory we have is a theory of structure and dynamics, of patterns and their evolution, of forces and fields and particles and their interactions. Nothing in any physical theory accounts for the subjective aspect of experience, the what it is like, the redness of red, the painfulness of pain. Structure and dynamics, however complex, seem to leave out the fact of experience. This is what David Chalmers calls the explanatory gap. The gap between any physical description and any explanation of conscious experience. Some philosophers argue the gap can be closed, that sufficiently detailed neuroscience will explain consciousness, that the subjective aspect will turn out to be the objective neural process correctly described. Others argue the gap is real, permanent, that consciousness is something the physical sciences, as currently conceived, cannot capture. These are the 2 poles of the debate. Neither has won. The question of whether consciousness can be physically explained or whether it requires something beyond physics is the deepest question in philosophy of mind, and it is not resolved. What happens at the center of a black hole? We have asked this before. Let me say it differently. The singularity at the center of a black hole is the place where our mathematics breaks down. General relativity predicts infinite density, infinite curvature. These infinities signal not a physical reality, but a failure of the theory, a place where general relativity needs to be replaced by quantum gravity, but we don't have quantum gravity, so we genuinely don't know what happens at the center of a black hole. Not approximately, not roughly. We don't have the equations. The center of a black hole is the most extreme environment in the universe, and we have no theory for it. Is there a physical theory of the mind? Not consciousness, we've covered that. The mind as a whole, thought, reason, belief, desire, intention. These are the objects of psychology and cognitive science. But what is their physical basis? Functionalism says mental states are defined by their functional role, by their causal relationships to inputs, outputs, and other mental states. The same mental state can be realized by different physical substrates. A human brain, a computer, a Martian made of silicon, truly minded. We don't know what is love chemically. We can describe the neuroscience of love, the dopamine of early romantic love, the oxytocin of bonding, the endorphins of companionship. But does this explain love? Does knowing the chemistry reduce the mystery? When you love a person, when their face in your mind produces something that words don't fully capture, is that just dopamine? Most scientists would say yes. And also, it's not just anything. The fact that love is produced by chemistry doesn't make it less real, less profound, less meaningful. The experience is what it is, regardless of its substrate, and yet the experience of love seems to exceed any chemical description, not because there is something non-physical in it, but because the experience, the feeling, is not the chemistry. The chemistry produces the feeling. The feeling is its own thing. The relationship between the neural processes and the experience of love is the relationship between the neural processes and any experience. Mysterious, unexplained, the heart problem again in its most personal form. Why do some memories last a lifetime? You have memories from childhood, vivid, detailed, emotionally charged. A moment at the age of 4, a holiday, a birthday, a loss. Something that happened decades ago that you can still see, still feel as if it were recent. And other memories from last week are gone. What determines which memories persist? We know emotion matters. Emotional events are remembered better than neutral ones. The amygdala, activated by emotionally significant events, modulates the consolidation of memory in the hippocampus. But why exactly? What is the neural mechanism of this modulation? Why do some emotional memories persist for a lifetime while others fade? The neuroscience of long-term memory consolidation is incomplete. The question of what determines the persistence of specific memories, why this moment, and not that one is not answered. What is the nature of beauty in mathematics? Mathematicians regularly describe their work as beautiful, an elegant proof, a beautiful theorem. They use aesthetic language, and they mean it, not metaphorically, genuinely. Euler's identity, EI pi plus 1 equals 0, is almost universally described by mathematicians as beautiful. Why? It connects 5 fundamental constants in an unexpectedly simple relationship. But what is it about this connection that produces an aesthetic response? Why should mathematics be beautiful at all? Why should the things that are true be the things that feel elegant? Why does beauty track truth in mathematics? Hardy argued that there is no permanent place in mathematics for ugly mathematics, that beautiful mathematics is lasting and important, that the aesthetic response of mathematicians is a reliable guide to mathematical significance. Is this just a feature of human psychology, or is it something deeper? A hint about the nature of mathematical reality? A reason to think that the aesthetic response is itself a form of perception, of something real? We don't know. The last questions, living with uncertainty. Why do we care about the future? We are mortal. We will die, and yet we care about what happens after we are gone. We plant trees we will not sit under. We care about climate change consequences, mostly felt by people not yet born. We care about the future of civilization, of the species, of the universe. Why? Evolution produces organisms that care about their genes' future. Caring about children and grandchildren is explained, but caring about the fate of strangers not yet born? caring about distant future scenarios beyond any genetic interest, caring about the fate of the universe in 1 trillion years. This exceeds any plausible evolutionary explanation. We care about the future in a way that goes beyond self-interest, beyond genetic interest, beyond any narrow evolutionary account. Why? What is the psychological mechanism? The philosophical justification? Is it rationale? Is it a mistake? The question of why we mortal creatures care about a future we will not see is one of the most interesting questions about the human mind, and it is not answered. What is the good life? Every society, every culture, every tradition, every individual has grappled with this. What is the right way to live? What does it mean to live well? Aristotle said, flourishing, the full actualization of human potential. The Epicurean said pleasure, the well-ordered pursuit of pleasure and the avoidance of pain. The Stoics said virtue, living according to reason, in accordance with nature. The Utilitarian said maximize happiness, the greatest good for the greatest number. Kant said act according to principles you could will to be universal laws. Religious traditions answer with obedience to divine command, or the cultivation of virtues, or liberation from desire, or love. None of these has won the philosophical debate. The question of how to live, what constitutes a life well lived, is the oldest question in ethics. And it is not settled, not by science, not by philosophy, not by religion. Each person must answer it for themselves, with whatever wisdom they can find, in whatever time they have. What is next? Science has been transforming our understanding of the world for 400 years, at an accelerating pace. The last 100 years have brought quantum mechanics, relativity, DNA, the structure of the universe, the origin of life, the nature of time. The last 50, dark matter, dark energy, exoplanets, gravitational waves, the Higgs boson. The last 20, the sequencing of the human genome, CRISPR, quantum computing, AI, the first image of a black hole, the detection of gravitational waves from neutron star mergers. The pace is accelerating. The tools are becoming more powerful. The questions are becoming clearer. What will the next 100 years bring? The discovery of dark matter, the solution of the consciousness problem, contact with another civilization or the confirmation of silence, a theory of everything, an understanding of the origin of life, the reversal of aging, something no one has yet imagined. Science advances in unexpected directions. The questions we are asking today are not the questions that will matter most in 100 years. The most important discoveries are the ones that come from unexpected directions, from experiments designed to answer one question that happened to reveal another, from anomalies, from observations that don't fit, from the thing that shouldn't be there. That turns out to be everything. The frontier is not the edge of the map. It is the edge of imagination, and imagination has no natural limit, closing the long, quiet 100 things science still cannot explain. Some of them small, the precise mechanism of a biological process, the details of a geological puzzle. Some of them medium, the nature of dark matter, the origin of life, the mechanism of consciousness. Some of them enormous, why there's something rather than nothing, the nature of time, the fate of the universe. And some of them intimate why we care about the future, what the good life is, how love works. I want to say something about what it means to live in the face of these mysteries. Not with anxiety, not with frustration, with something more like gratitude, because the mysteries are not absences, they are invitations. Every unsolved problem is an invitation to think, to wonder, to explore. Every we don't know is a space that the mind can inhabit, can play in, can push against. The scientists who spend their careers on these questions, on consciousness, on dark matter, on the origin of life, are not failing. They are succeeding at the hardest thing there is. They are holding the question open, refusing the premature answer, sitting with the uncertainty, not collapsing it into false simplicity. That is not a failure. That is intellectual courage of the highest order. You have been listening to 100 questions, 100 places where the map runs out, where the confident statements end and the genuine not knowing begins. And I hope that somewhere in all of that not knowing you have found something, not an answer, a feeling, the feeling that the universe is deeper than it looks, that there is more beneath every surface, that the questions go all the way down, and that this inexhaustible depth is not a problem. It is the most beautiful thing about existence. Let your breathing slow now. Let the question settle, not to be solved tonight, just to rest in you. The way questions rest in the minds of the people who have carried them for decades, with care, with patience, with a kind of love for the not knowing itself. You are made of the stuff the questions are about. Atoms forged in stars, biology shaped by billions of years of evolution, consciousness of unknown origin, in a universe no one fully understands. All of it, the mystery, the wonder, the not knowing, all of it, here, in this room, in this body, in this breath. You are the universe asking itself questions that it cannot answer, and finding that beautiful, finding that enough, more than enough. Close your eyes, rest in the mystery. It has always been with you. It always will be. The questions will be there in the morning. They are patient. They have waited this long. Sleep now